Yeah, I want to go, yeah, I go back where where I am. I lost where I am. Just a minute, I'm sorry. Yeah, here I am. I don't want to go with all the examples here, the theorem. If you have a commutative semigroup with 0 and n is a positive integer, and this set, remember what is the ZNS, the zero divisor, ZNS, you go to the zero divisor of the semigroup S, and you start taking power x to the n and so on, and the cardinality is bigger or equal to 2, then the following are equivalent. This is to be connected. Look at number 1 and 4. This is for any commutative semigroup. For the N-zero divisor graph of S to be connected, the classical zero divisor graph of Sn, of the set Sn, has to be, or I mean, remember Sn, it's a set, but it's a semigroup. It's the same as the N-zero divisor graph of S. And I mean, these two tell me exactly when this graph is connected. That means when the N-zero divisor graph has to be the classical zero divisor graph of Sn. Otherwise, these graphs will not be connected. Okay, so let's move on. Yeah. Okay. What about the distance? Remember the distance between, in general, in a graph, like if you have two vertices, let's call them A and B. What is the distance between them? Is like the number of the minimum edges you need to cross to go from A to B. I mean, this is like in the street language definition. I mean, like if you want to go from A to B, then you need to cross edges. The minimum number of edges that you need to cross or to walk on to go from A to B, this is the distance. Okay? For a reduced commutative semigroup, it turns out that it's always true that the gamma, the N-zero divisor graph of S, is equal to the classical zero divisor graph of Sn. By the previous theorem, that means the graph has to be connected. And the nth distance between x to the n and y to the n has to be the same distance as between x and y. And this is kind of interesting here in this, if you think about it, because remember that x to the n and y to the n are element in Sn. And this d index by n is just telling you that I measure the distance inside Sn. I want to go from xn to yn as element in Sn. The distance, it will be the same as the distance between x to the n and y to the n in the classical zero divisor. I mean, you might think maybe the distance will be shorter since I'm taking powers of x to the n and y to the n. No, in case, and remember, reduced mean the only nilpotent element is 0. I don't have nilpotent element. Okay? And the diameter of the nth zero-divisor graph is always less or equal to the diameter of the classical zero-divisor graph, less or equal to 3. All right? Okay, let's look at this result. If you have a reduced commutative semigroup and n is a positive integer, and you selected two vertices, x and y, in the zero divisors of the semigroup S, and definitely x and y, none of them is 0, and assume the distance is 3. Then x to the n, y to the n, they will be distinct, and the nth distance between x to the n and y to the n stay 3. And they have the same diameter. Okay? Here, you're going to see this is not always true. In fact, we have examples, but this is assuming that you have at least two vertices where the distance between them is 3, and I'm measuring the distance here in the classical zero-divisor graph. So if I go to the N-zero-divisor graph, the diameter stays 3. Okay. Here is a complete answer for reduced commutative ring. If the diameter of the mth zero-divisor graph is 3, then the diameter for any n, just, like if you assume you check that for m equal 2 or 3, just for one m, then the diameter will stay always 3, and it will equal to the diameter of the classical zero-divisor. So number 3 is kind of unique, nothing changed. But let's look at number 1. Assume the diameter is 1 for some m. Then the diameter of the classical could be 1 or 2. And for every n after m, it will be between 1 and 2. And we have examples. We have an example of a ring where the diameter for some m is 1, and for another m is 2, and the diameter of the classical zero-divisor graph is 2. Okay, so for 3, nothing changed. For 1, things might change. What about if the diameter is 2? By the way, maybe I should mention what we mean with diameter. Maybe you know that from basic graph theory. I mentioned the distance. The diameter, as you expect, you take the supremum. And here I can use maximum because it's less than infinity. So it's finite always. So like you find the distance between every two vertices, and you take the maximum of the distance. That will be the diameter of the graph. Okay? The maximum of all distances. And let me remind you again, the distance is measured like like if I say the distance between A and B is 3, that means I need to, there are 3 line segments, like I can go from A to A1, A2, and then B. Here I'm using a 3 line segment. And when I say the distance is 3, that means I cannot go from A to B by two-line segment or one-line segment is the minimum number of line segment I need to use in order to go from A to B. And the diameter, you take the maximum of all these distances. If you look at C, so here is an answer for 3. For 1, things change. For number 2, oh, I run out of time. How much time left for me? Oh, I'm going very slow. Sorry. Uh, okay. So let me tell you about the girth for reduced commutative ring. Remember that the girth is the shortest cycle in the graph. If the girth of the classical zero-divisor is 3, then the girth stay 3. You see number 3 kind of interesting number. Nothing change. It will change in case of 1 and 2 and 4 and so on. Okay, I will end up with some references. And of course, if you are interested, I will be happy to send you a preprint or, of this paper. And I thank you again, and I thank the organizer again. Yes, yes, this is the part that we have it, like we connected the girth with the structure of the group of the ring for us. I mean, as I told you, there are 24 pages. I cannot talk about that, but definitely that's in fact why we study graph. I mean, not just here is the graph. So what? There are some connection between the ring structure and diameter, girth, and so on. And in fact, proving some, even the one you just saw so far, we use some, ring properties and things to, I mean, like if you observe, like number 3, nothing change. So that definitely tell you about the structure. There is something, it's not a completely graph theory thing. Even if you read the proof, you see there is, and we are using properties and structure of rings and so on. But definitely we have complete answer for some ring structure when diameter is given or when girth is given. Or maybe I should give that part instead of this part. Anyway, it's too late. Okay, thank you.